All right, so our class today is on work and energy. Now, these ideas were introduced to measure the relative efficiency of steam engines. Energy is the ability to do work, and when work is done, there's a change in energy. That's a bit of a circular definition, but there you have it. So, for instance, if a person does work throwing a ball, that means that the energy that they had in their muscles, which is chemical energy, that chemical energy gets converted to motion energy. And motion energy is kinetic. Friction takes that mechanical energy, that motion energy, and converts it to thermal energy. And the symbol for thermal energy is Q. If you lift a book, then again, you're using the chemical energy in your muscles, and that's the chemical bonds in the food that you eat, and converting that to height energy. Height energy is PE. So, when work is done, energy changes form. Work is the product of force and displacement, and as we've just said, when work is done, energy changes form. The units here are joules, and a joule is defined as a Newton meter. So that's our first equation for work. There will be several to follow. We define power as the rate of doing work, so that's the ratio of work over time. And the units then are energy units over time, joule per second, and that's a watt. Now, since work is the product of force and displacement, we see that power will be force times displacement over time. But of course, displacement over time, that is the velocity. So we can see that we can write power as the product of force and velocity. Really, this is the average velocity because displacement over time is the average velocity. If it's moving at steady speed, there's no difference, but if its speed's changing, then we would average the velocity there. Now, because powers work over time, we see that the energy will just be the product of power and time, and so that's how you'd convert from a power to an energy. In biological physics, the efficiency ratio is really important. Efficiency is a Greek letter eta, and it's sort of like an N with a long tail, and it doesn't have any units because it's a ratio of two energies, the useful energy output to the energy input. Now, the useful energy output is usually the work that's done, so we can write the efficiency ratio like this. Now, of course, the energy of the universe must be conserved, so if you're taking a certain amount of input energy and converting that to work, there must be something left over, and what's left over is typically thermal energy, Q. Now, in the context of the human body, this would be the food that you ate. This would be walking around, running, climbing, pumping blood, breathing, and then this is body heat. The thermal energy keeps us warm. So let's imagine that you eat a hamburger and then go jogging. Your muscles are 20% efficient. What happens to the food energy of that hamburger? Well, with 1,000 calories, you have just ingested 4 million joules, because a food calorie is 4,186 joules. Okay, so I think there's a picture of a burger that's missing here. 1,000 calories is a lot of food energy. So this is probably like a double Big Mac, a milkshake, and an extra large fry. Okay, so here's your energy input. The food energy of 4,000 calories. Sorry, 1,000 calories or 4,186,000 joules. Now, the efficiency is 20%, or as a decimal, it's 0.20. And you're going jogging, so that will be the useful output. So that's the work you did in moving yourself along the track. Your center of mass goes up and down as you jog, so there's changes in potential energy. So what this tells us, then, we can rearrange and solve for work, cross-multiplying. How much work did you do? It's the product of the efficiency and the food energy. So the efficiency is 0.20. The food energy is the 4,186,000 joules. So the amount of work that you did can be calculated. All right, so that works out to be 837,200 joules of work done. So, of course, energy is conserved. So how much thermal energy is created as you're jogging? Well, you burned off 4 million joules, and only 837,000 was converted to useful work, so the remainder was thermal energy. Okay, so you can pause the video and then try this one. After you've had a try, start the video up again and try and see how well you did. You can compare your solution with mine. So pause the video at this point and try this problem. All right, so now presumably you've tried it, and I'll proceed with the solution. So we have 2.5 calories of food energy. That'll be the energy input from our skittle. We have to convert from calories to joules. Each calorie has 4,000 joules of food energy in it. So that gives us 10,465 joules of input. Now, we'll use the efficiency ratio next. It's the energy output, which is the useful work, over the energy input. So the amount of exercise that you'll need to do depends on the 20% efficiency, and then this amount of food energy that we want to burn off. And that tells us that we have to do 2,093 joules of useful work. Now with the Stairmaster, this work is potential energy, or you could say that the force is going to be your weight. And for a 60 kilogram person, that'll be 60 times g. Now, of course, the work is the force times the displacement. So the displacement will be the work required over the force exerted. So you need to do 2,093 joules of work lifting a 60 kilogram person, or a 60 times g. So putting in 9.8 newtons for g, you find that you're going to have to move 3.56 meters. Now, each cycle on the Stairmaster, it's 35 centimeters up and 35 centimeters down, so that's 0.70 meters. So the number of steps that you need to take then is 3.56 meters of total displacement over 0.70 each step. That's about a little bit more than 5 steps. Okay, so you'd have to do 5 steps on the Stairmaster, lifting your entire body weight up the 35 centimeters and then going back down the 35 centimeters. Let's now consider two-dimensional problems. And this would be a typical force problem you've encountered before. You're pushing on an object on an angle. Now, there are other forces that act on it. There's a normal force from the surface. There is, of course, weight, the gravitational pull of the Earth. And there will be a friction force here, resisting sliding. Now we see that we're pushing on an angle. We're partly pushing down, and that's the y component of applied force. And then we're partly pushing to the right. That's the x component of applied force. Now in terms of trig, this is the adjacent side, so this will be the cosine component. In terms of trig, this side is opposite, so this will be the sine component. So we're going to write force equations here just because it's a good review and will be useful for us. We're going to add up the forces in the y direction. So my y-axis is going to be straight up like this. My x-axis will be to the right. So in the y direction, normal force is upwards, so that's positive y. Gravity or weight is downwards, that's negative y. And then this y component is also downwards. So the plus just means up, and the minus just means down. Now the sum of the forces in the y direction has to equal the mass times the y acceleration, but the y acceleration is 0 because this object doesn't move up or down, so we arrive at this statement here for y forces. For the x forces, we only have two. There is the x component of applied force acting in the positive x direction, and then in the negative x direction we have friction. That equals the mass times the x acceleration. Now that x acceleration doesn't have to be 0, it could be non-zero. But the y acceleration does need to be, since this object doesn't move up or down. Now we see in that force analysis that there are some forces perpendicular to the direction of motion, such as the normal force, the weight, and the y component of applied force. They actually do no work at all, because there's no displacement in that direction. So there's no energy change associated with those forces. A force opposite to motion, like friction, well, it, strictly speaking, does negative work because the system loses energy as a result of that force. Then there's a force parallel to motion, like the x component. That's the one that does positive work. So work then is done by the force component that's parallel to the direction of motion. And we'll write this in another way shortly, but it's really a conceptual equation. We have to find the component that's going in the same direction that the object is traveling, and then we can evaluate the work that's done. An important result relating work and energy, we said that work was an energy change. Really, we're going to be more precise here. We're going to calculate the total work, and the total work is the work done by the net force. Now, net force according to Newton's second law is mass times acceleration. And then I'm going to just use a different color here. I'm going to put in a factor of 1/2 here, and I'm going to put in a factor of 2 there. Now, clearly, I haven't changed the expression because the 1/2 and the 2 would cancel and go back to the previous expression. But now, these three terms here, they are the difference in velocity squared, if you remember your kinematics. And then I still have the 1/2 m out in front here. And then this is 1/2 mvf squared minus 1/2 mvi squared. And so we see that is just the change in kinetic energy. So what we've proven then by this derivation is the total work, which is the work done by the net force, is the change in kinetic energy. So if we add up all the work done by all the forces, that's kinetic energy change. Okay, so here, a little exercise for you again. Draw the force diagram, write the force equations, calculate friction, and then try and find the work by the applied force, the work by friction, the work done in total, and the final speed of the mass. So pause the video, try this, and then play it to hear my solution. All right, so hopefully you've had a try on the problem and are now just watching my solution. I'll start with the force diagram, and this really is the same as the one on the previous page. There's a normal force, there's a weight, and there's friction. We need our force equations. First of all, in the y direction, there's upwards normal force, there's downwards weight, it's 6 kilograms, so that's 6 times 9.8, g is 9.8, and then it's downwards Fy. Now net force always equals ma, but the acceleration in the y direction is 0. So this gives us a value for the normal force. When we solve, we bring these two over to the other side. And of course the y component is going to be downwards. This is the opposite side, so this will be the sin component. It's 20 sine of 15. And that works out to be 63.96. So the upwards normal force balances the downwards weight and the downwards force component of the applied force. Now that's important because friction is mu times the normal force. So the mu constant is given as 0.1. We multiply by the normal force, 63.96, and this tells us the amount of friction, 6.396 newtons of friction. Our x force equation just tells us Fx minus friction equals ma. All right, so now we're ready to find the amount of work that's done by the applied force, friction, and in total. Okay, so work done is going to be the component parallel to motion. Well, the component parallel to motion is the x component. And so that is going to be 20 cos 15 times the displacement, which is given as 5 meters. This works out to 96.6 joules of work done. Next, the work done by friction. Work is a force times the distance. Friction's opposite to motion, so that means, strictly speaking, the work should be negative. Now we've calculated the force of friction as essentially 6.4 newtons. If you didn't get 6.4, it's probably that your y force equation was wrong here. So check your y force equation carefully. The displacement is still 5 meters, so negative 32 joules of work. So that means that 32 joules of thermal energy are produced at the expense of some mechanical energy, some motion energy. So the total work then is just the sum of those two, and that works out to be 64.6 joules of total work done. You can also find the total work by taking this net force and multiplying by the displacement. Oh, I guess this wasn't really A, B, and C. This should have been little bullet 2 and little bullet 3. Because now for part B, to find the final speed of the mass, several ways. One way is you find the acceleration and then do kinematics, or the way we'll do it, because it's a bit faster, is to say that the total work is the kinetic energy change, 1/2 mv squared. Because it starts out at rest, this whole term just disappears, and we can find the final speed. 64.6 joules of work on a 6 kilogram object. Divide by 3, take the square root, gives you a final velocity of 4.64 meters per second. All right, so another problem for you to try. So once again, pause the video, draw the force diagram, and check the force write the force equations. Then find the force in the rope. You need to pull the mass up an incline at constant speed. That's important. And then find the work done by the various forces, the pulling force, gravity, and then the total work done. When you're done, play the video, compare your answer with mine. All right, so hopefully you've had a chance then to try this on your own. Let's start with the force diagram solution. Try and do it precisely here. So there'll be a normal force here, perpendicular to the ramp. Then there's a weight force straight down towards the center of the earth. And then because it's a frictionless ramp, we're done at that point with forces. Now, we're going to need to resolve this rope force into components. Firstly, there'll be a component parallel to the ramp. Then there'll be a component perpendicular to the ramp. That one didn't work out right. Okay, then with gravity, there'll be a component that is perpendicular to the ramp. Down this direction right here. And then there'll be a component that is parallel to the ramp. Oh, this is slow. Okay, let's just go back to the pen tool. Okay, that was a bit painful, but I went away and fixed it up. So here, this is the tension in the rope, and we can see there's an X component here that's going to be T cos 30, and a Y component here that's T sine 30. Here's normal force, here's weight. It's a 4 kilogram object, so this is 4 G's of weight. Now this angle, it turns out, is always the same as the ramp angle, so it's 20 degrees. So this is going to be 4G cos 20 in the Y direction, and then this X direction force pulling it down the ramp is the same as this side of the triangle. That is an opposite side. That's a sine component, so this is 4G sine 20. All right, so now we write our force equations. In the Y direction, perpendicular to the ramp, this way, we've got normal force, we've got the Y component of tension, both upwards, then we've got downwards, 4G cos 20, and those are balanced because there's no motion that way. In the X direction, let's take the X-axis to be going up the ramp. In the X direction, we've got the X component of tension in the positive X direction, and then minus this 4G sine 20 gravity component that acts down the ramp. Now that equals ma, but because we're told it's constant speed, there's no acceleration, so that is also 0. So there's our force diagram, there's our force equations. That's what we're going to need to solve this problem. Now the first thing we're asked for is the amount of force in the rope. We see that our second equation here will enable us to solve for the tension, because we can put into here the fact that the X component of tension is just T cos 30. So this equation here then reduces to, so it reduces to T cos 30 equals 4G sine 20. And you solve that for tension, and you get 15.5 newtons. So that's the force you need to pull it up the ramp. Then for the work, well, work is only going to be done by the X component of tension. So it's the X component of tension, the T cos 30, that does work, and then you have to multiply that by the displacement, and the displacement was given as 6 meters. So this is 15.5 cos 30, the X component, times 6 meters. That works out to be 80.44 joules of work done. Now for the work done by gravity, it'll be the X component of gravity times the displacement, but the X component of gravity is down the ramp, opposite to the displacement. So strictly speaking, gravity is negative, does negative work in this case. So the sine 20 component is the one along the ramp. We multiply that by 6 meters of displacement, and we get negative 80.44 joules. So that the total work done in this case is actually 0 joules. Now why is that? Well, because total work, including both of these forces, we just proved was the same as the change in kinetic energy. And because this object is going at steady speed, there is no change in kinetic energy here. So it's not surprising the total work done is 0. So to summarize then, when we're dealing with components and two-dimensional forces and work, we do positive work in this case, no work in this case, negative work when the force is opposite to motion. And here we have to find this component that's parallel to motion. That turns out to be F cos theta. So the work in this case is F cos theta times d. But really, that explains these first three pictures as well, because here there's a 0-degree angle, and the cos of 0 is just positive 1. Here the angle is 90 degrees, and the cos of 90 is 0, so this expression would give 0 work. Here these two vectors are pointing opposite to each other, so there's 180 degrees between them, and the cos of 180 is negative 1. So negative work done as we expect. So this relationship summarizes all of this diagram. However, it's important to note that this angle is very specific. It's the angle between the force and displacement vectors. That means we can't just unmindfully apply this relationship. It's better for us to have internalized this concept. But nonetheless, this is a nice succinct way of writing out this idea.